let's say I've got some basis B, and it's made up of k vectors. Let's say it's v1, v2, all the way to vk. And let's say I have some vector A, and I know what A's coordinates are with respect to B. So this is the coordinates of A with respect to B are c1, c2, and I'm going to have k coordinates because we have k basis vectors, or if this describes a subspace, this is a k-dimensional subspace. So I'm going to have k of these guys right there. And all this means, by our definition of coordinates with respect to a basis, this literally means that I can represent my vector A as a linear combination of these guys, where these coordinates are the weights. So A would be equal to c1 times v1 plus c2 times v2 plus all the way, keep adding them up, all the way to ck times vk. Now, another way to write this is that, let me write it this way. If I had a matrix where the column vectors were the basis vectors of B, so let me write it just like that. So let me say I have some matrix C that looks like this, where its column vectors are just these basis vectors. So we have v1, v2, all the way to vk. If we assume that these are, let's say that all of these are a member of Rn, then each of these are going to have n entries. So it's going to be an n by k matrix. Each of these guys have n entries, so we're going to have n rows, and we have k columns. So let's imagine this matrix right there. Another way to write this expression right there is to say that A is equal to the vector c1, c2, all the way to ck multiplied by this matrix right there. This would be equal to A. This statement over here and this expression over here are completely identical. If I take this matrix vector product, what do I get? I get c1 times v1, plus c2 times v2, plus c2 times v2, plus c3 times v3, all the way to ck times vk is equal to A. We've seen this multiple times in multiple different contexts. But what's interesting here is this expression is the same thing. And it's really, I'm just applying new words to things that we've seen probably 100 times by now. We can rewrite this expression. This is C. And remember, C is just a matrix with our basis vectors as columns. C is equal to this guy. This is just the coordinates of A with respect to the basis B. So C times the vector that has the coordinates of the vector A with respect to the basis B, that is going to be equal to A. That is equal to A. Now, why did I go through the trouble of doing this? Because now you have a fairly straightforward way of, if I were to give you this, if I were to give you that right there and say, hey, what is A if I wanted to write it in the standard coordinates, or with respect to the standard basis, which is just kind of the way we've been writing vectors all along, then you just multiply it times this matrix C, this matrix that has the basis vectors as columns. If the other way, if you have some matrix A, if you have some vector A that you know can be represented as a linear combination of B, or it's in the span of this basis vectors, then you could solve for this guy right here to figure out A's coordinates with respect to B. And so this little matrix right here, what does it do? It helps us change bases. If you multiply it times this guy, you're going from the vector represented by coordinates with respect to some basis, and you multiply it times this guy, you're going to get to the vector in just with standard coordinates. So we call this matrix right here change of basis matrix. Change of basis matrix, which sounds very fancy, but all it literally is a matrix with the basis vectors as columns. So let's just apply this a little bit to see if we can do anything vaguely constructive with it. Let's say that I have some basis. Let's say B for basis. Let's say I have two vectors. I'll define the vectors up here. Let's say vector 1 is, let's say we're dealing with R3. So vector 1 is 1, 2, 3. And let's say that vector 2 is 1, 0, 1. And let's say I'm going to define some basis b as being the set of the vectors v1 and v2. And I'll leave it to you to verify that these are not linear combinations of each other. So this is a valid basis that, these aren't in any way linearly dependent. Now, let's say that I know some vector that's in the span of these guys. Let's say that I know some vector that's in the span of these, and all I know is how it happens to be represented in coordinates with respect to this basis. So let's say I have some vector A, and when I represent the coordinates of A with respect to this basis, it's equal to, I don't know, let's say it's 7, 7, minus 4. So how can we represent this guy in its standard coordinates? Or, what is A equal to? What is A equal to? Well, you could just, you say, oh, well, A is equal to 7 times v1 minus 4 times v2, and you'd be completely correct. But let's actually use this change of basis matrix that I've introduced you to in this video. So the change of basis matrix here is going to be just a matrix with v1 and v2 as its columns. So 1, 2, 3, and then 1, 0, 1. And then if we multiply our change of basis matrix times the vector representation with respect to that basis, so times 7 minus 4, 7, 7 minus 4, we're going to get the vector represented in standard coordinates. So what is this going to be equal to? What is this? We have a 3 by 2 matrix times a 2 by 1. We're going to get a 3 by 1 matrix, which makes complete sense because we're dealing in R3. This vector right here, A, is going to be a member of R3. A is a member of R3. So when we write it with standard coordinates, we should have 3 coordinates right there. Now, when we represented A with respect to the basis, we only had 2 coordinates because A was in the plane spanned by these two guys. Actually, this is a good excuse to draw this. So let me draw it in 3 dimensions. Let's say the span of v1 and v2 looks like this. The span of v1, v2 looks like this. And let's say this is the 0 vector right there. So this right here is the span of v1 and v2. Or another way, this is the subspace that B is the basis for. And so we know that A is in this guy. So let's say v1 looks like this. Let's say v1 looks like this, and that v2, I'm not even looking at the numbers. I'm just doing it fairly abstract. Let's say v2 looks like this right here. Now, the fact that A can be represented as a linear combination of v1 and v2 tells us that A is also going to be in this plane in R3. And in fact, it's 7 times v1. So 7 times v1. So it's 1 v1, 2 v1s, 3 v1s, 4, 5, 6, 7. So it's 7 in that direction. And then it's a minus 4 in the v2 direction. So that's 1 in the v2 direction. This is minus 1 in the v2 direction, minus 2, minus 3, minus 4. Or we could do it here. 1, 2, 3, 4. So our vector A is going to look like this. It's going to look like this. It's going to sit on the plane. So this is our vector A. It's going to sit on the plane. And when we represent it with respect to this basis, when we represent its coordinates with respect to our basis B, we say, okay, it's 7 of this guy. I'm just doing this abstractly. Don't pay attention to the numbers just now. I just want to understand the idea. We say it's 7 of this guy minus 4 of this guy. So it takes you back here and you get this vector, which is in this plane. So we only needed 2 coordinates to specify it within this plane because this subspace was 2-dimensional. But we're dealing in R3. And if we just want the general version of A in standard coordinates, we'll have to essentially get 3 coordinates. And I want you to understand that A is sitting on this plane. This plane just keeps going on and on and on in all of these directions. A actually sits on that plane. It's a linear combination of that guy and that guy. But let's figure out what A looks like in standard coordinates. In standard coordinates, we get the first term is going to be 1 times 7 plus 1 times minus 4. So that's going to be 3. Then you get 2 times 7 plus 0 times minus 4. That is 14. And you're going to get 3 times 7 plus 1 times minus 4. So 3 times 7 is 21. Minus 4 is 17. So A is the vector 3, 14, 17. That is equal to A. Now let's say we wanted to go the other way. Let's say we have some vector. Let me pick a letter I haven't used recently. Let's say I have some vector D. Let's say I have some vector D, which is 8, 8, minus 6, 2. And let's say we know that D is a member of the span of our basis vectors, the span of v1 and v2. v1 and v2. Which tells us that D can be represented as a linear combination of these guys, or that D is in this subspace, or that D can be represented as coordinates with respect to the basis B. Remember, the basis B was just equal to the set of v1 and v2. That's all the basis B was. Now, we know that if we have our change of basis matrix, times the vector made up of the coordinates of D with respect to B. So let me write that down. D with respect to B is equal to D. We know that. We know if we have this guy's coordinates and we multiply by the change of basis matrix, we'll just get the regular standard coordinate representation of D. Now in this case, we have D. We're given this. We of course know what the change of basis matrix is. So if we wanted to represent D in coordinates with respect to B, we're going to have to solve this equation. So let's do that. So our change of basis matrix is 1, 1, 2, 0, 3, 1. And we're going to have to multiply it sometimes some coordinates. This thing right here, we can represent it as, I'll do it in yellow. We're going to represent it. We're going to need two coordinates. It's going to be some multiple of v1 times plus some multiple of v2. So it's c1, c2. And we know it has to be two coordinates because this matrix vector product is only well defined if this is a member of R2, right? Because this is a 3 by 2 matrix. We have two columns here, so we have to have two entries here. And then that's going to be equal to D. That's going to be equal to D. So we have 8 minus 6, 2. And so if we figure out what this vector is, we've figured out what the representation or the coordinates of D with respect to B are. So let's solve this. So to solve this, we can just set up an augmented matrix. That's just our traditional way of solving a linear equation. So what we have 1, 1, 2, 0, 3, 1. And we augment it with this side right there. So we have 8 minus 6 and 2. And let's keep my first row the same. So I have 1, 1, augmented it with 8. And let's replace my second row. with the second row minus 2 times the first row. So I'm going to get 2 minus 2 times 1 is... Actually, let me do it the other way. Let me replace my second row with 2 times my first row minus my second row. So 2 times 1 minus 2 is 0. 2 times 1 minus 0 is 2. 2 times 8 is 16. Minus 6 is 10. Now let's replace the third row with 3 times the first row minus the third row. So 3 times 1 minus 3 is 0. 3 times 1 minus 1 is 2. And then 3 times 8 is 24 minus 2. 3 times 8 is 24 minus 2 is going to be 22. See, it looks like I must have made a mistake someplace because I have these two would lead to no solution. So let me verify what I did, make sure I didn't make any strange errors. So the second row, I replace it with 2 times the first row minus the second row. So 2 times 1 minus 2 is 0. 2 times 1 minus 0 is 2. 2 times 8 minus 6. So there's my error. That's equal to 22. That was my error. So these two things are equivalent. Now, I'll do one step at a time. Let me divide. Let me replace my third row with my third row minus my second row. Just get it out of the way. So I'll keep this 1, 1, 8, 0, 2, 22. And then the third row is going to be my third row. I'm going to replace it with my third row minus my second row. So it's going to be 0, 0, 0. So that just gets zeroed out. Now let me divide my second row. Let me divide my second row by 2. So I get 1, 1, and 8. And then this one becomes 0, 1, and 11. And then, of course, the third row is just a bunch of zeros. And then let me keep my middle row the same. So it's 0, 1, and 11. And then let me replace my first row with my first row minus my middle row. So 1 minus 0 is 1. 1 minus 1 is 0. 8 minus 11 is minus 3. And I'll keep my last row the same. So I've put the left-hand side in reduced row echelon form. So this right here is essentially telling me my solution. I know that C1, the solution, so I could write it this way. I could write that 1, 0, 0, 1, 0, 0 times C1, C2 is equal to minus 3, 11, 0. Or another way of writing this is that 1 times C1 plus 0 times C2, or C1 is equal to minus 3, right? 1 times C1 plus 0 times C2 is equal to minus 3. And then we could have, and then we have 0 times C1 plus 1 times C2 plus 1 times C2 is going to be equal to 11. So our solution to this equation, is minus 3, 11. Or another way of saying this is that if I wanted to write my vector d in coordinates with respect to my basis b, it would be the coordinates minus 3, 11. So if I want to write my vector d in coordinates with respect to my basis b, it's going to be equal to minus 3, 11. Which implies, let me write it this way, which implies that d is equal to minus 3 times vector 1 plus 11 times vector 2. And I'll leave that for you to verify. But just like that, using this change of basis matrix, we can go back and forth. If you have this representation, it's very easy to take the product and get the standard representation for d. If you have the standard representation, or the coordinates with respect to the standard basis, it's very easy. Well, it's a little more involved, but then you just solve for your coordinates with respect to b.